the ith rectangle? What is the area of the ith rectangle?
Oh, just that and then times its height.
Yeah, it's just the width of the ith rectangle. So the width of the ith rectangle is delta x sub I. Yeah. Times the height of the ith rectangle. And the height of the ith rectangle is f of c sub I. Is everyone okay with this? I'm doing this in a very, wait, are you also in 9th period? Or are you in this class?
She's in this class.
I'm so confused.
She's in this class. She just got to answer right.
Alright, cool. So does this make sense to everybody? It's the width of the ith subinterval times the height of the ith subinterval. And the height of the ith subinterval is just the value of the function at the right endpoint. Okay, so now do it. We have formulas for these things. And now the radical just melts away, right? Did you guys get what I got? And if you now take the limit as n goes to infinity of this whole thing, what do we get? 2/3. Okay, victory. Did anyone think, is everyone cool with this? Okay. They would think of there's like another kind of semi-creative way that we could have solved this problem that involved a lot less work. Yeah, right.
This is why I like it. So you look at root x, right?
Yeah, it's like root x.
Yeah, and then you think to yourself, thank you. That it's like the inverse of x squared.
Yeah.
Which means that if you have like a box that's like 1 by 1,
Yeah, and we
it
do.
should be all the area that x squared isn't.
Yup.
And then you
Yup.
just
It's
like
like
1 minus x
what's
squared.
that famous line about someone asked some I think it was like some French sculptor how do you make an elephant? He's like, just take out all of the things that don't look like an elephant. And then
What?
Does anyone know who said that? I started to try to do a French accent, and then I thought better of it. But yeah, just, how do you sculpt an elephant out of a block of stone? You take out everything that doesn't look like an elephant. So yeah, if we what he says is, I don't know how to do that, but I do know how to do this, and like, you know, inverse functions, blah, blah, blah. This is just going to be this is just like kind of the parabola y equals x squared between 0 and 1. And that I do know how to do because it's a polynomial. So I just learned that that's 1/3, but I could have calculated that directly with my old methods. That would have been faster. All right. I think it looks like it. This is it. So you actually just learned a fascinating fact, which is that the parabola y equals x squared divides the unit box in a like, you know, into like a 1/3, 2/3 area. So I think that's kind of interesting and sort of pretty. Okay. Good. This is one way in which we have generalized our concept of finding the area under the curve. Moral of the story number 1, we do not necessarily need rectangles of equal widths. Okay, let's take a little bit of a more theoretical look now at this whole process. And this is just kind of more practice with subintervals and stuff. So, all right, so let's do this. So we're going to do this whole thing in general. So in general, suppose we have a function f, and we're going to do this on the interval a, b. And let's just say for now, that f is positive on this interval. And what I would like to do is I'd like to find the area under this curve. And I'd like to contrast Rm with Lram. Okay. Let's do it. So I'm going to first do this with Lram, and then I'm going to do it with Rm. So this is the Lram method. Cool. And then here I'm going to do Rm. Maybe I'll do this one first. So we're going to take the interval from a to b, and maybe the function looks kind of like this. Maybe here the function looks kind of like this. Okay, and we're going to use n rectangles. So if we are going to use n rectangles, then what is delta x, the width of each rectangle? Yeah, it's going to be the total width, which is b minus a, divided by the number of subintervals n. So delta x is going to be b minus a over n. Everybody cool with that? So now we're back to equal width now for the moment. All right, so we can draw some beautiful pictures. Here, I'll do Rm first. So I kind of go this. So here's like my first rectangle. Here is my next one, etc. And then I guess do something like that. Okay. So cool. Can you guys now write me an expression? Like I said, skipping more steps every time. Can somebody write me an expression in general for the sums of all of these rectangles? You understand what I'm talking about? We're kind of just generalizing this procedure. So what are the sums of all of these rectangles? I don't know, like basically I'm going to have n of them, right? And what's the area of the nth rectangle?
B minus a over n.
It's going to be b minus a over n. Can I just write delta x just for simplicity's sake? Maybe should we do a little bit of like preliminary work? Maybe we should do a little bit of preliminary work. That would be helpful. This is a. What's this first point? The first point I care about, because it's the first point I'm going to plug into the function. A plus b minus a over n. Yeah, I'll just write delta x just because. Okay. And then what's the next point which I plan on plugging into the function? A plus 2 times delta x. Yeah. What's the next point?
3 times delta x.
A plus 3 times delta x. Is everyone okay with this? It's just like what we've been doing, right? And now we go all the way dot 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 to the end. What's the last one be according to our pattern? When we get to the nth rectangle, A plus, how many times have I scooted over now? n times. Yes, this is n times delta x. And of course, since delta x is b minus a over n, when you multiply n by b minus a over n, you get b, right? Which is exactly what you're supposed to get. Is everyone with me? Yeah? Okay. So, can you write me a formula in general for, can you, with that little bit of help, can you now write me a formula in general for the sums of all these rectangles? It's going to be the sum from I equals 1 to n of, what's the width of the ith rectangle? Delta x. And what is the height of the ith rectangle? F of a plus, and I've moved over delta x I times. Right. So this is exactly all the stuff we've been doing. We're now just doing it in a sort of theoretical, abstract manner. Okay, leaving that on the board for the moment. So that's sort of like Rem in general for some function in general on the interval from A to B. Quickly now, let's do Lrem. Well, if I do Lrem, then like it looks kind of like this or whatever. And now we have something that looks like that. Okay, so now it's a little bit different because now the first number I want to plug in is that one, right? And now it's this next one. This is going to be a plus delta x. This is going to be a plus 2 times delta x, etc. But now since I'm using the left endpoints, the formula is a little bit more complicated, right? Let's see if you can do this. If I'm going to take the sum now from I equals 1 to n, what's the width of and now I need an expression for the area of the ith rectangle. The width is still delta x, but the height is this is like gets like technical, but I think you guys can handle it. It should be f of a plus. Yes, good. Yep, a bunch of you were saying it. I minus 1 times delta x, because now when I'm on the ith rectangle, I have moved over by delta x I minus 1 times only to get to that point that I plug in. Okay, I should probably draw these. All right, so this is all cool, and by the way, for any particular n, these are going to be different, right? They're going to be different numbers that I get. But does somebody have a bold and wonderful conjecture that they would like to make, which is sort of like kind of obvious and common sense, and you really wish that it were true? It like should be true, hopefully. Laura?
The limit as n approaches infinity of both become minus 3.
Wait, what's it?
Laura says, though these sums are different, if we let the number of rectangles approach infinity, I think that they're the same. Yep, seems totally reasonable, and in fact it is true. So I'm going to take the limit as n goes to infinity of this. I'm going to take the limit as n goes to infinity of this. And if I do so, wait, no, you can say, but no, I have no control over you. You have to. You should go somewhere else. But
We're getting more people
I know, it's getting weird. I think you guys have to start paying me now.
Don't go to
All right. So.
Okay,
Okay, go, guys, fast. I don't want to like run out of time. So good. Yeah, this is true. This is awesome. This is actually a theorem. Let's just call it like theorem. This is a theorem of, it doesn't really have a name. It is a theorem of advanced calculus. It's the kind of thing that you would prove in some kind of like advanced college level class. And actually, this is a special case. I'm not gonna write it down. This is a special case of a more general theorem. Okay, so more general theorem even says, well, okay, what we're now going to do is we're going to draw pictures again of a function in general on the, a function f on the interval AB, and let's let the function be positive just for ease. Yeah. And try to draw the same function twice. Okay, and now what we're going to do is we're going to draw rectangles in a weirder manner. What we're going to do now is we're going to divide up the interval up into subintervals. I think I'll use 4. Right? And see, this is fun. Watch this. What we're going to do now is we're going to apply the minimum rule.
Okay.
And the minimum rule says, do not necessarily use the left endpoint. Do not necessarily use the right endpoint. Use whatever is smallest. This is the thing that was in the book. In fact, should we like write some stuff down? I feel like we should write some stuff down. Ready? I'll give you some definitions. Let m sub i be just equal the x coordinate of the minimum of f on the ith subinterval. Yeah, it was kind of in the last section, but now we're talking about it like for real. Let m sub I be the x coordinate of the minimum of f on the ith subinterval. In other words, for each subinterval, let little m sub I be the x coordinate of the place where the function is smallest. Is that one with me? Okay. And let big M sub I be the x coordinate of the maximum of f on the ith subinterval. And perfect raise before that we are. Okay. And what we're going to do now is I'm going to choose the height of the rectangle to be whatever it needs to be so that the rectangle is as small as I can make it. So over here, what is on this first if here I'm using the minimum rule, on this first subinterval, what x value should I use? A, yeah, the left endpoint. So I will draw a left endpoint rectangle here. How about the second one? It's a little awkward on that picture.
I don't see it.
Okay, let's draw it a little bit better so it does something cool. Patching this up. Suppose that it has some like relative max that happens somewhere in the middle of that second subinterval. Oh wait, I'm supposed to be doing the minimum, aren't I?
Yeah.
Blah, 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 blah. All right. Which should I use? Left endpoint or right endpoint? I think left. I don't know. It's hard to say. Yeah, left. So left. Okay. But now, what do I do when I get over here? What now? Now I should use the right one. Yeah. And now what do I do? This is where it gets exciting. On the fourth subinterval, what x coordinate do I use?
Minimum.
Yeah, wherever that relative minimum is, right? See what's going on here? Picture's worth 1,000 words. Cool? Say cool.
Cool.
Okay, good. All right, and now we will apply the maximum rule. And in the maximum rule, again, I'm going to split this up into 4 subintervals. Sure. Okay. So now, when I apply the maximum rule, which x coordinate should I use for this first subinterval? The right one. On the second subinterval, what one do I use? Yeah, that relative max, right? Everyone see what's going on? And then over here, I'm going to use, for the third subinterval, left endpoint, and the fourth subinterval, use the right endpoint. Okay. All right. So I could always apply the LREM rule, or always apply the RREM rule, or I could choose on a subinterval by subinterval basis. I could choose the height of my rectangle to be wherever that function is minimum or maximum. Okay, we can write this out also. So what is this area? This area is going to be, Rohan, talk to me. Sum from I equals 1 to n, still have n rectangles. What is the width of the ith rectangle in the minimum rule?
Delta x.
Still delta x. And what is the height of the ith rectangle? Arun, can we give Mateo head check? That's it.
Yeah, he's good.
What is the minimum? What is the height of the ith rectangle following the minimum rule? Someone, not necessarily Rohan. Yeah, f of little m sub I. Exactly. That's why I defined this kind of little bit of notation, right? M sub I is the x coordinate of the place of the ith subinterval where the function is minimum. So f of that just is that minimum y value. Follow? Okay, and then over here, the sum is going to be the sum from I equals 1 to n of delta x times, what's the height of the ith of the rectangle on the ith subinterval? Yeah, f of big M sub I. Because I defined big M sub I to be the place where the y value is largest, so that is the largest y value. Okay. Do you have a thought, probably, about what is going to happen in this situation? Say something smart again. Laura, same thing.
The limits will be the same even though they're not the same.
Yeah, do you sort of feel it? Do you sort of feel like that should be actually right? So, is this just like wrong?
Oh.
No, that's right, that's right.
No,
That's right.
what did that,
That's right, that's right.
oh wait, the
If they
mid.
want to-
Yeah, the mid, okay.
Looks weird though, man. Alright, so yeah, these are the same. So theorem, if you take the limit as n goes to infinity of this, and you take the limit as n goes to infinity of this, these are going to be the same. In other words, it does not matter, all this kind of stuff gets washed out in the end, as long as you take an infinite number of rectangles, even if you always take the minimum or always take the maximum, everything's going to be fine. And again, like I said, this is like a theorem of advanced calculus or whatever that you would prove in some kind of analysis class. All right, one more step on this subject. Not only could I always choose the left endpoint, always choose the right endpoint. I could invent some other weird rule, like always choose the midpoint or something. I could always take the minimum. I could always take the maximum. I could also just pick in each subinterval whatever point I want. Let x sub I, just x sub I star, I call it, be an arbitrarily chosen x value in the ith subinterval. And the last picture is one in which I just do whatever I feel like doing. So I take this function and I do this, and I split it up into n, and then basically I choose on the first subinterval just some arbitrary guy. Calvin, I'll just call this like, I don't know, I'll just, in this first subinterval, I'll call that x sub 1 star. I'll just pick like that point or whatever. In the second subinterval, what should I pick? Yeah, maybe I'll just decide to pick the right endpoint just this time, just because I feel like it. And then in the third subinterval, I'll pick like, I don't know, that one. So that's x sub 3 star. And in the fourth subinterval, I'll pick like that one. I can pick whatever point I want to be representative of that function on that subinterval. And this is all okay as long as what? N goes to infinity. Yeah, and someone explained this to me a little bit. Why should this, there's actually something to be said about this. How do I know that these numbers are all the same? If you accept that thing as a theorem, yeah, why did you? Give me the answer in one word.
What?
Give a one-word answer.
Limit.
Line.
It's the same point.
Say
Definition of
infinity. That's a word.
They all
Yeah. Why should what I get when I pick whatever point I want be the same as what I get when I always pick the minimum or always pick the maximum?
How do you say it? What's the word he's looking for?
Yeah, there's like a word.
What's the word?
Okay, you'll see. It'll come to you in a second. So watch. I'm going to give you like a little proof of this fact. Ready? Look at the ith subinterval. F of x sub I star, the value of f somewhere in the ith subinterval is guaranteed to be between f of little m sub I and f of big M sub I. Because that's the way I have to find these things. Stand up for like 5 minutes. No, Calvin, this is falling asleep. Yes, thank you. He said it. Yeah, the value of the function at some arbitrarily chosen point must be between the minimum value of the function and the maximum value of the function. And now we're gonna like do some stuff to this, right? One thing we could do is multiply through by delta x. So these are now heights of functions. Now this second statement becomes a statement about rectangles. Right? This now says, this second statement, if we want to interpret it in some kind of like geometric way, this says that the arbitrary rectangle is somewhere in between the minimum rectangle and the maximum rectangle. And as that's true for every single subinterval, I can now add them all up. Do you guys see how I really have like n of these inequalities? And if I add up all n of these inequalities by properties of inequality, what I really have is that the total sum of f of m sub I delta x has to be less than the total sum of the x sub I star delta x, which is indeed less than or equal to total sum.
Squeeze theorem.
And yes, it's all come to you now. Yeah, now we apply the squeeze theorem, right? I have just proven to you that the sum, that this arbitrary sum is between the minimum sum and the maximum sum. So if you already accept this as the theorem, that was supposed to be an F. if you already accept that, if you already accept that as a theorem, then now we just apply the squeeze theorem. I'm kind of too lazy to write it. Can I just move on? If you take the limit of all three sides of this inequality, the squeeze theorem says that if these two limits are the same, then this limit must be the same also. Okay, so Shivani, in two ways we have now expanded and made more abstract our process of finding the area under the curve. The first way in which we made it more abstract is we said we do not necessarily need rectangles of equal widths, right? The second way we've made it more abstract is to say that I don't even need to follow a general procedure. As long as in the end I take the limit as n goes to infinity, I can choose any point that I want, anywhere in the middle. Those are called sample points. Okay, we are now ready to talk about one of the most fundamental objects in calculus. These things called Riemann sums. This is classic calculus.
I saw it.
Riemann. This is named after Bernhard. I think it's Bernhard, right? Bernhard.
I just check every like time we switch it.
Bernhard Riemann, and Bernhard Riemann, German. I believe he's German. I hope he's German. German mathematician of the 19th century. Really, he's up there. What's that? I don't know. Oh yeah, I need all your homeworks. Everyone who was here at a certain point got extra credit. I guess you should all get it, right?
No.
No? I don't know, whatever. Yeah.
But it's only five homework points.
Yeah. Anyone who was here earlier and didn't give me or anyone who was not here at the very beginning of class, can I have the homework that was due today?
Yeah.
We also got cookies.
There were also cookies. Yeah. Can you put them in the pile over there? Wait. Stay focused. Half an hour left. Building to an exciting climax here. All right. What are Riemann sums? All right. It's difficult to give a formal definition, so I'm not going to really give a formal definition. I'm just going to like talk it out what it is. All right. Yeah. So this is what a Riemann. Here's how a Riemann sum works. First of all, I have some function f. So f is I'll just throw in continuous because probably that's a thing. F is continuous on some interval ab. So take some continuous function on some closed interval. Say check.
Check.
Good. Now I'm going to do something with this interval. What I'm going to do is I'm going to partition it in a certain way. Because, as we discussed a half an hour ago, I may split up my subintervals in any way I choose. Okay, so watch this. I am going to take the number line take A, the left endpoint of my interval, easy. Take B, take A, the left endpoint of my interval, and B, the right endpoint of the interval. And what I'll now do is perform a partition. And a partition is simply a way of splitting up the interval from A to B into subintervals. So I'm just gonna like do some things, you know? Like I'll call that x1, I'll call that like x2. Some of them might be kind of far apart, some of them might be close. Like who knows? You just kind of like do whatever you want. Dot dot dot. And then it's customary to call the lat B to call that like x sub n, and it's customary to call A x sub 0. So this is a partition. And I'll say it one more time. A partition is just a way of splitting up an interval into subintervals. Bless you. And what we learned earlier is I do not have to use subintervals of equal widths. I can use subintervals of unequal widths. Okay, but now there are some good ways of doing this and some bad ways of doing this. So there's no technical term for this. So I'll just say that a partition is a good partition. Technical term. A partition is good if it has that property that we talked about from the beginning of class. That property that, as n goes to infinity, the width of even the widest subinterval goes to 0. So a partition is a good partition if, as n goes to infinity, the width of even the widest subinterval goes to 0. Did I say infinity? I meant 0. In other words, if as n grows larger and larger, all the subintervals are shrinking in pain because they are shrinking. If all of the subintervals are shrinking down to 0, then that's like a legit partition and you're good to go. All right. And now, the final thing that we do is in each subinterval, we choose a sample point. So we choose a sample point, x sub I star, from each subinterval. Okay. All right. If you understand this sort of technical theoretical background, I'm now going to tell you what a Riemann sum is. A Riemann sum is the stuff that we've just been doing for the last 2 days. A Riemann sum is a sum from I equals 1 to n of functions or a function evaluated at a sample point chosen from the ith subinterval times the width of the ith subinterval. This is called a Riemann sum. So all the sums over here on the back board are Riemann sums. So, okay, cool? Okay. Even though, so this is in some ways, this is not really new. This is just the things that we've been doing, but now I'm